All right, so chapter 4, diode. So we have studied linear circuits so far, where we have a resistance and we generally use, uh, for the most part, Ohm's law, and we get a linear output on the out, which is a function of the input multiplied by gain. But there are many more functions which are non-linear that we want. For example, we want to convert from AC to DC or vice versa. Or we may want to do things where we are manipulating some functions, integration or differential equation or amplification, where signals have many different waveforms, or digital logic. So these are nonlinear functions. If you want to have 0 and 1, those we define the ranges, what can be considered as 0 and what can be considered as 1. So that's where a device like diode comes in, which is a nonlinear device, which has a nonlinear behavior. And in the most fundamental form, we write a diode like this, a triangle with a line to the front. We have the notion of, we call it forward bias and reverse bias, depending if the positive terminal is coming to the anode and the negative terminal is connected to the cathode. So cathode is that line side. So this is, if this is connected to the negative terminal, this is to the positive terminal, we call it forward bias. Hold on, some other app started. Now, so this is a simple way we are saying that when it's forward bias, it conducts. When it's reverse bias, it does not conduct. So if I draw an IV characteristic, that would look like this. So you have current, you have voltage, and we say, okay, it has no current flowing if it's reverse biased, and if it's forward biased, we get unlimited current. So that's what it is showing. When you say reverse bias, we can show it as an open circuit, which means there is no connection between the input and output, and hence what we would get in the output circuit is there'd be no current flowing. Now, if I say this, then we can simply look at it as a resistance with very high value or a resistance that has no value. And we'll look at more at how we can model this. But these are just two modes of operation which are showing that ideal diode and external circuit can result into a current flowing or no current flowing. So what we are doing here is, for this case, we are showing there's 0 volt across the diode. So whatever you get is flowing through. And this is something which is the Ohm's law, where you can just get the current from V over R. So that everything then flows. But in this case, we say, okay, this would not conduct any current. So whatever the voltage is being applied would stay as it is. So that has an application in circuits. We'll see where we can use them in logic circuits. We can use them as voltage limiter or even current limiter circuits. All right, so the most fundamental application of a diode is use as a rectifier. A rectifier is, we'll look at more detail of rectifier, but rectifier is where we would have current which will conduct in one way, only in the forward bias, and not in the reverse bias. Now, when you say this, then for every diode, we have to see what kind of voltage is it experiencing, and we have to keep our ground in mind when we do that. So for example, this first one, when there is a positive voltage on this side, you have output voltage, which through this resistance is grounded. So which means when there is positive voltage, this would be conducting. But when if the voltage goes minus, this would be reverse bias. And in this case, no current will be conducted. So you see this part, there is no current that's conducting through there. So if you would apply what we just discussed on previous slide, you can, in forward bias, you can just show it as a short circuit. You can just say, okay, this is just behaving like a resistance of 0 ohms, which means no voltage drop across there. Or you can, for the negative signal, when the diode becomes reverse bias, you can say this is open circuit. So note here, we haven't put any values on voltage right now. So when we put the numbers, then we have to see the numbers and see which numbers are higher to see if it's forward biased or reverse biased. But in very general sense, we would just call it, if it is forward bias, as a short circuit, and open circuit if it is reverse bias. And that would then translate into the output from this input. So that's the upper plot is for input, the lower plot is for output. Can everybody hear me? All right, very good. So you can see the slide as well. All right, I cannot see some of you. So where do we use? So one application is here is what we call as a simple limiter circuit. So what it's doing is, so when the input voltage is greater than this power supply, which is shown here, if this is larger, it would be forward biased. But if it is smaller than this, it would be reverse biased, right? So if I can again use what we have done before, reverse bias would be open circuit, forward bias would be short circuit or closed circuit. So what it is going to do, the diode will turn on when the diode turns on, when the input voltage is greater than the power supply. The voltage that you can see on the output is limited to only this power supply value. Let me clean it and we can see what I'm talking about. So what does this circuit do is that the voltage that we get is only going to be limited to the number that, according to our design, is this number. It's not going to go above. Because if it goes above, then what we do is we get only this and nothing more than that. So while it is going to positive, the value which is greater than this guy, it is gradually going to start conducting, and then it's going to stay just at that value. So that's the use of diode as a power limiting system. And the simple output and input relationship, we draw it as voltage versus voltage. And the reason is that tells us the characteristics, like before for an amplifier, what kind of input will result in what kind of output on the especially when the signal is sinusoidal. So here there are a couple of things. If you would write it down in the form of the relationship, and if we have more than one diode, so what we are doing is for any current through any diode, we would use the relationship to find out the difference between two voltages, in this case, input minus the power supply divided by R. So when there is the volt, and now we are talking about the sine wave, a circuit where the input is taking positive and negative signs. When V plus is greater than VI, this is reverse biased and this is forward biased, right? So you see in either case, one of the diode would be either conducting or off. Let me show this again from the previous slide. When this guy is larger than this guy, we have forward bias. That would be the case for this circuit. In this case, second diode is open circuit. There's no current flowing there. Now, when VI is smaller than the power supply, then we have this, sorry, not that, then we have this guy where D2 is short circuit and D1 is open circuit. But when both voltages are equal, there's no current flowing. So that would be the case for this guy where there will be no current flowing. So now the output of this circuit in either side, plus and 5 and minus 5 is limited by this circuit. So the output is this guy, which is because of this diode, our outputs, these are, these pictures are overlapped. The outputs will always going to be within 5 volt, right? So as the signal on the input side changes from plus to minus or minus to plus, we'll see that the maximum would always stop there because the voltage drop across the diode is 5 volt and it's going to restrict it to that. All right, now that's where our nodal analysis knowledge comes in. Let's pick up one of these. So our output voltage, we have to look from the output side inwardly and then see what kind of circuit do we see. So if I am, let's pick this D, if I'm looking from this side, what I see is node, and then I do my nodal analysis and I see that these are two resistances which are seen as parallel. So in that case, I see this one is the one which would be the limiting voltage because of that resistance in parallel with that. We'll get more into that on the analysis as we pass through the introduction part here. All right, questions, comments? So you guys have seen diodes before, I can imagine, right? So we'll be doing lots of analysis. So this is, and when you say we do lots of calculations. So this is question from example 4.4. And the question says, let me take the question out. This exercise 4.4. Oh, it's figure 4.4 and it's example. What example is this? Yeah, it's exercise 4.4. Find the value of I and V in the circuit shown here. What we need to find is current and voltage. So, for example, this guy. All right, so the voltage difference between +5 and -5, it tells us that there is it's forward biased, right? So one side is the anode side is high, the lower side is grounded. Current would be simply the difference between the two voltages divided by the resistance, right? So 5 volt minus 0, which is ground, divided by 2.5 kilo ohms. Kilo will flip it and take it up, and that would become milliamps, right? So now we have considered this to be the 5 volt. The voltage across the diode would be 0. Because when you look at from this side, you see this one is the higher resistance, so the voltage drop occurs around this, and this is forward bias. It's short circuit. There's no voltage drop across this. Let me come again. So we got the current is straightforward, but for the voltage, we have to see this is short circuit, so there is no voltage drop across this. So hence this voltage is 0, and here we just calculated 2 milliamp is the current that's going through that resistance. All right, the second one is showing now this is reverse biased, right? So this is an open circuit, which means whatever voltage gets to this node is going to show across these guys, and that is 5 volt. Because now these two resistances are in parallel, and if they are parallel, the voltage across them would be the same. Now, what is the current here? Current open circuit would be 0 amp, because there is no wave, no place for this current to go. Are you with me so far? All right. Third example. We have this guy as forward biased, right? And because this is less than 0, -5. So it's now this guy is forward biased, but the current of course will flow from higher potential to lower potential. So the voltage here will be 5 volt. But the current will be 0 amps. Because the current has to flow towards ground. So this current is 0. Now in this case, this is now reverse biased. So voltage here is 0, but the current is, of course, the difference between the two, 0 minus -5 is, and 2.5, it's 2 milliamps again. All right, so we're just considering DC right now, and we'll introduce a concept of small signal that may ride over DC, and in that case, we ignore the DC part and we do it differently. But we'll see that as well. All right, so when we look at the IV characteristics of a diode, we have a few things that go in there. For example, the forward bias current, the reverse bias current. How do we calculate those? The forward bias current is when V is greater than 0, it's written as IS e to the power V over threshold voltage minus 1. Let me break it down what's going on here. So this is what we call scale current or saturation current. There are different ways how we take it. And this is the fundamental current that would be there when you turn it on. And then there is an exponential rise to it. So hence the exponential part to it. And this exponential part is, this is the applied voltage. And this is what we call as threshold voltage. And threshold voltage is a constant for diodes. It's and temperature. Sorry, the threshold voltage is dependent only on temperature. This guy is a function of the diode dimensions, cross-section area, and all those things. So it depends on maybe a bigger monolithic device versus a smaller monolithic device. So it goes down to the material things to it of a diode. Now, this is VT. Threshold voltage has a dependence on temperature through this relationship, Boltzmann constant times temperature divided by Q. For our purposes, we take it as 25 millivolt for 20 degrees Celsius, right? So whatever temperature in Fahrenheit, room temperature. So we use a constant value for this, 25 millivolts. Now, as the current goes above this saturation current, we see that this is the way how we would calculate it. Now, this is an exponential part, and we put I1 here just to take care of this small part, which is very close to zero. But we can ignore it because as the exponential region is much more bigger. So we can just write it as I almost equal to ISE to the power V divided by VT. And that makes our other rest of the analysis much easier. So we're talking about forward bias right now. And this relationship is good for many decades of current. Right now, it looks like it just goes up, but when you magnify it, we see there is a dependence, and there's kind of a linear relationship between those two. Sorry, exponential relationship between those two. All right, so in the forward bias, then there are these voltages that we come across, 0.5 volt and 0.7 volt. We call it break-in voltage. The voltage at which so 0.7, we take it from that calculation of VT, KT by Q. So this is what will tell after which the diode turns on, right? So how do we see the dependence of this current with the voltage? Let's just look at the forward bias. When we have a relationship for a current, let's call it one current, I1, we can say, okay, this is in response to one voltage. I call it V1. And let's consider another voltage where we get another current, we call it I2. So same relationship, but now instead of V1, I write V2. Right? So I'm trying to see what is shown in this figure also, that if there is small change in voltage, how does the current behave with respect to that? We can take the ratio of these two And the right-hand side is exponential, of course. The IS will get canceled out, but I get e to the power V2 minus V1 over Vt. So this is exponential relationship, and I can do my log thing, and I can get V2 minus 1 is equal to 2.3 Vt log of I2 over I1. So difference between two voltages can result into a log dependence over their differences. So when we plot it, we can see that for a decade change in the current, like if it goes from 1 to 10 or 10 to 100, the voltage drop changes by 2.3 times of the threshold voltage, which we know this, guys. So this is 60 millivolt. Okay, what we have done is we have found that if you change the current by a decade, the voltage will change by 60 millivolts. So this is a good characterization or a good knowledge about diodes. So we can predict their behavior of how they would change if you change the current through them by changing the resistance in the external circuit. So that's the forward bias thing, that how this would change, how the current would change if you, how the voltage would change if you change the bias. Now, in the reverse bias, we have current, we call it very close to that scaling current, up to a point, what we call as breakdown. And breakdown, there are different mechanisms, what happens in breakdown. But for the reverse current, we take this to be the current, and minus is the just giving us the direction of the current. And this is, IS is on the order of 10 raised to power minus 14 amps to 10 to the power minus 15 amps. And this, ideally, it should be open circuit, but this current is because of leakages and all that. And this is what we call as breakdown, or knee current as well. We write it as VZK also. Zener, K is knee, which is we say, okay, this is the knee of the IV plot. So there are different ways how we look at this. All right, so this is just the behavior of the diode. Okay, now this plot is showing dependence on temperature. We'll not concern ourselves with that, but this VT has temperature dependence. We'll just take room temperature. We'll take 25 millivolt for our calculations and applications. All right, so now how do we model the behavior of a diode? So this is a simple way. We'll have power supply. We say there's some resistance in the circuit, and we have a diode operating with its forward bias and reverse bias. And the exponential, and there are two ways how we take it. We say, okay, there is an exponential model, which we just discussed, where the diode current is just a function of the diode voltage and threshold voltage. Now, if I apply Kirchhoff's loop equation here, I can find my current depending on whatever is the flow going on in here, and that would be ID equals VDD minus the diode voltage divided by R. So now these are two equations. This is an exponential equation, and this is a linear equation. what do we do here? So what we do is we plot those of these behaviors, and one would be behavior which gives us an exponential plot, and the other one is which gives us a linear plot, right? So this is voltage and this is current. Now this cutoff point is when your voltage is zero, when the voltage across diode is zero. So this is VDD divided by R from this relationship. And this is just VDD. This is just the voltage, the supply voltage. And now this point is called the Q point. And this is the operating point that we want our diode to operate at. So load line, there's a concept called load line where we are modeling the two ways how we can characterize the behavior of diode. And from that, we can find out, okay, what would be the sweet spot for the diode to operate, where it does not saturate and it turns on and delivers the best that it's supposed to. Now, if you look at it, this is what we call as load line. And this Q point over the load line is where this exponential model interacts with the linear model. And that gives us the diode characteristics. There's much more cleaner version of what I just plotted. Now, how do we find out the current flowing through a circuit? We would apply the Kirchhoff's loop, and that gives us numbers that we can look at the circuit and decide if those numbers make sense. So it's called iterative method, where we plug in that approach and we see if it's giving us what we expected it to give. So let's look at an example 4.4. Let me get that from the book. All right, so it says that determine the diode current and the diode voltage for the circuit 4.10, which is what we just saw, this same guy. And let me plot it here. So just a simple circuit where we show resistance, we draw a diode, and we have a power supply, and this is R current, diode current is ID, diode voltage is VD, and power supply is VDD. And the question says, with VDD 5 volts and R is 1 kilo ohm, 1K, and it has a current of 1 milliamp at 0.7 volt. All right, so first again, the loop analysis. Can somebody identify what would be the different voltages in this loop? So one is this guy, and one is this guy. How do we write them? So how do we find current through these two? It will be power supply minus the voltage drop across diode divided by the resistance 1 kilo ohm. And that gives us 4.3 milliamp. Now, how do we know this number is right? We can use that knowledge what we had, that if you change the current through a decade, the voltage should change by 60 millivolt. So which was V2 minus V1 equals 2.3 Vt log of I2 minus I2 divided by I1. So we can use this to see if our numbers are right. And Vt, we know, is 60 millivolt, right? So from this, I can find out V2, and what all I'm doing is I'm bringing this V1 to the other side, the voltage that we are using, and I can find that this would be 0.738 volt. Now, is this showing a change in my current? I can see if the diode current is changing, and we see that this voltage across diode is still in the same ballpark, 0.7, which is its operating voltage. And if I plug in this number, we can see that we still get the same current as we got before, which is 4.262.
Excuse me.
Yeah.
Where'd you get the 2.3 in the bottom equation?
So this is what we saw here. From this relationship, we applied the log here, and we got V2 minus V1 equals 2.3 Vt log of I2 over I1.
Okay.
So that's a factor which came from here. So I'm just using that relationship to verify my number on the current that I got from just applying the Kirchhoff's loop model on this. Right? So we established something that from this guy, that for a decade change of current, which is log. So log is a decade plot, right? You go from 10 to 100 to 1,000 to 10,000. For that change, there is voltage change of 60 millivolt. So we are using that knowledge to verify that if the current that I got from directly applying the Kirchhoff's loop equation on this model is indeed the right model to get us the current. All right. So these two numbers are close enough. So it seems, so this was just by applying the loop equation, and this is, we have seen, okay, if we use that relationship where we can change the voltage, do we still get the same current or not? So there are two models now, and we have applied one of that already. So either we take it, we say that there is a constant voltage drop across a diode, and we take that to be 0.7 volt. And we will use that for going forward. Remember, at start, we was just taking a diode to be either an open circuit with no voltage drop across it. or we were taking it, we were taking it at open circuit where there was no current flowing. So the whatever is the applied voltage, you get it on the other. And we were taking as the forward bias as short, right? So there was no voltage drop. But there are two models how we do that, and we have to take care into our analysis the voltage that's being consumed or dropped across a diode. So this is where we then take this exponential kind of rise to be a step function. And we say, okay, the voltage drop across is just 0.7 volt. So in this case, then, like we just saw, if you have a power supply of 5 volt, for example, and then you have a voltage drop of 0.7 volt, and with whatever resistance, we can find the current through a diode, right? So in wherever we see the application, this would help us find the current through a diode. So whatever voltage is coming in or applied across minus 0.7 and divided by the resistance. All right, so for many times, if we have higher voltages, much bigger voltages, we can just ignore sometimes 0.5, but that's not what we'll do. We'll use it whenever we are doing our analysis. All right, so when we say that that's the voltage drop across every diode, then we see how we calculate, especially if they are in series. So what is the overall voltage drop across each one of those? So that's where let's take a look at this situation. So it says provide an output voltage 2.4 volt. Assume that all the diodes have 0.7 voltage drop at 1 milliamp, right? So now this is the current, right, through a diode, 1 milliamp. And this we said is IS e to the power, here it is given 0.7 divided by VT. Remember the original relationship for the forward bias current of diode, right? So at any unknown current, this would be IS E VD or VT, right? So that's the original relationship that we are using. Now, if I combine this, we can find an unknown current from this, and that'd be E VD. So what I've done is I'm just equating these two, minus 0.7 by VT. So here, let me just correct this. So this one was, I have to put the value here. This one is 1 milliamp. All right, so now for the output of 22.4 volt, so the total drop across each diode, the total what we want is 2.4, right? So then across the each one, this would be then 2.4 divided by 3 diodes. It should be 0.8 volts. Now, what is the current through each diode? Let's bring this in and using 0.8 now. 0.8 minus 0.7 divided by threshold voltage 25 millivolt. We can, now we are using others at volt, so we'll use this as volt as well. And that gives us 54.6 milliamp. So to achieve this guy, we have to have current of 54.6 milliamp. Now that would then tell us what should be this resistance. So now I have to plug in, let me use the next one. That would be 10, which is the power supply, minus 2.4, the voltage drop across these three diodes, divided by the current, which we just found, 54.6 milliamp. I'll just write MA. And that then tells us the resistance that we have to use have to be this number from calculation of this. You with me on this? Can you guys hear me?
Yes.
All right. So we know it's 0.7, but since the change is, so we have to go back to the fundamental equation, and then we have to use the difference between our standard relationship and this. Excuse me. All right, so I see some chat messages. All right, Matthew asked me, where did I get my 0.025? VT, threshold voltage. We discussed that threshold voltage is KT by Q. It's a standard thing. And it is a temperature dependent quantity. Boltzmann constant times temperature divided by electron charge. For room temperature, we use 25 millivolt. Some places in literature, some other courses, you'll see they'll use 26 millivolts. So it's here we will use 25 millivolts. So this is the VT, which is in the exponential of the current relationship for forward bias. Right? With me on this? Sorry, sometimes I feel I'm going too fast, but yeah, just ask me a question and let me know if things get really fast. I don't want to do that. Don't want to rush it. All right. So now I thought this should probably will deal with it later, the reverse bias. While we are doing forward bias, let's stick to forward bias and we'll come to this slide later. All right. So now, so far we have done just DC, right? So one voltage and we find resistance and all that. But many times it's not DC. We have to deal with signals. And what we are saying here is a small signal model. Yeah, one can say, why small signal? What does it mean to have small signal? We'll look at what is the condition for a signal to be small signal and why we are starting with small signal for now. There is a condition that needs to be met for us to be able to analyze it in a way that we are going to do it. So again, we have a picture where we have a DC voltage VDD, which is giving a current ID. Now, in ID and VD, the diode voltage and diode current, we have seen how we calculate. We can use the Kirchhoff's loop model, but if they ask us to change something, we can plug in the exponential model also. And we have seen an example where we use both, and we got similar number. Now, if this guy is composed of a small signal, I don't want to call it AC signal because that would have a periodicity and all those. So let's just say that there is a small change that comes with it, and we call it delta VDD. Now, with that, there will be a small change in the diode current also, right? So we call it delta ID. Now, the voltage of the diode would then change by an increment delta VD. So how do we find the values of these small changes? So that's where we develop this small signal model for the diode, and we see that what are the changes and how delta VD is kept small. All right, so let's start writing some fundamental relationships for that. So we can say, okay, VD, now it is time dependent, right? So we can write this signal and I'm writing small v here. Now this would be, we can say, okay, this is the DC VD plus now a small change in the incoming signal. So you have to see by capital D and small d, it's just to distinguish that what is the voltage changing across VD and what is the time varying signal. So this is for the time varying. Instead of writing deltas, this guy, I'm just going to write it VDT. All right, so now what is the current for a time varying signal? I can write down the same fundamental current for diode in forward bias ID, but now I have to write it time dependence. And that becomes again the basic current times e to the power. Now instead of just VED, I have to write this guy, which is composed of the DC and the small variation divided by VT, right? So now everybody knows what is VT, threshold voltage, temperature dependent parameter, 25 millivolt. All right, so then now if I put my VD, this guy here in this exponential, so it's going to become expanded just a little bit. So it's going to be IS e to the power capital VD plus small v small d t dependence all divided by VT. So it's all in exponential. Right? When I can split now exponential into two parts, which is IS e to the power VD over VT and e to the power VD over VT. Right? But if I look at this guy is my original fundamental relationship for the current through a diode, right? So I can just replace that with that guy, and I can write it as the current through diode, just like as is, times e to the power small signal divided by threshold voltage. Oops, I deleted a little bit more. Are you with me going from here to here? That was a simple diode current, simple DC diode current. But now we have this factor that it's multiplying with VD. Okay, now the question comes that if I keep this VD very small, so small that I say VD over VT is very, very smaller than 1, I can expand this exponential in terms of a series, in terms of a geometric series, and I can get the terms that come out of that. This is now where we say, okay, this VD is small signal. Small, then the whole function can be small. So then I can expand this exponential into a series. And what do I get? I'm gonna clean some of the part here. Let me clean this. I'm gonna write this part. So if I do that, my original relationship for current with small signal variation becomes simplified, and I get ID times 1 plus VD over VT. I just truncated the remaining smaller terms, just took the first two terms in there. So this is what we call, and let me put this almost equal to the sign here. So this is called small signal approximation. It is valid for signals whose amplitude are smaller than about 5 millivolts, right? And VT is still 25 millivolt here. So now if I expand this relationship, what I get is ID, okay. The left side is still the same. I'm going to put an equal. So I'm bringing it down here. Now this will become equals ID plus ID over VT times small vd, the time varying signal. This is a very important relationship. What we are doing here is we are now introducing a small signal being a time varying signal. So hence what we are doing is we are bringing the concept of ultimately an AC signal. But right now we just call it small signal. Now this ID, small ID, the right hand side tells me now that the signal is riding on ID. So your DC signal plus this time varying signal. So signal current component is directly riding or superimposed on the DC current ID, capital I, capital D. You with me? Louis, Matthew, Elisa, Brandon? I can't see you, Brandon. All right. So when I look at the camera, then I'm looking at you guys because your pictures are right behind the camera on my monitor. And this is my iPad where I'm writing, so I have to keep my eyes down. So, and I have my notes on my left side as well. So we love electronics, but we all have to have cues and write down these things so we do our analysis right. Now, ID is showing up in two of those things. What is the significance of ID? ID, now this part is because of this small v, small d is become the small signal contribution in our analysis. And that's what I want to expand on, because that's going to help us now analyze difficult things. So I can just write it capital ID plus the current because of small signal, right? Because and then the left side is big I, big D, the total current. We take this ID. What I've done is I've written this guy to be equal to right. So I've just written that as small I, small d like that. And this relationship is interesting because the signal voltage VD is related to this guy. But if you think about Ohm's law, this can be, if it was on left hand side, this would have been resistance, right? V equals IR. If I look from the left, from the right side, V equals IR, but this is next to V. So we call it conductance, not resistance on this side. And this has units of mho, just instead of OHM, we are saying MHO, mhos. And this part is called small signal conductance. Resistance versus conductance. And inverse of this is called small signal diode resistance. All right, these 3-4 lines are very important, what I just said. So if you look at this guy, let me change the color. If you look at this guy and look from the right hand side with Ohm's law, it should be V equals IR, but R is not on the other side. There's this ID or VT which is on the right hand side. So on this side, this is called conductance, and its units are mhos, MHOs. What it does is if you flip it, we get what we call diode small signal resistance, and we write that. I'm gonna clean some more room here. We write that as RD, small signal resistance, and that's VT over ID. And the value of RD is, if you look at it, is inversely proportional to the bias current ID. If you look at this, it's inversely proportional to VT is constant, right? So threshold voltage is constant for a given temperature. Let me write down this. This is IR. So higher the diode current, smaller the diode small signal resistance. What do we do with this? This helps us in our small signal analysis. If you now go back to this idea of load line, I'm going to clean this up as a little bit thing about small signal resistance. The diode is operating at a DC bias point, right? Q, which we call that's the intersection of these two plots. Now, if we superimpose this small VDT here, we will get a triangular waveform. So now that's 4.40. Let me make sure I get the right. Yeah, so that's, if you remember this, we have the figure. Yeah, this guy, I was looking for this guy. So we have now this guy riding on top of your Q point voltage. So this is now going through a small signal variation around that Q point. And that's kind of a spiky wave, which is coming because of that small signal riding on top of the DC signal. And the amplitude is so small that it is going like this, but we can approximate it like this. Although signal is going like this, but what we are doing here is we are approximating it with a kind of a short, almost linear segments that are pieced together. That makes our analysis much easier going forward. All right, so any questions so far? So now we're going to apply these fundamental relationships that we have developed, especially the signal current component, capital V, with this component, which is directly proportional to VD, from which we have found that this is small signal conductance, And the reverse of this is the diode small signal resistance. So I just flip it and I get this guy. So whenever you have diode current, we can simplify the figure and our analysis just by using RD, the diode small signal resistance. Now, when we have a system where we have a small signal variation, there are a couple of steps we take to simplify our analysis. We just eliminate DC signal or DC sources. So these steps are important. Now, when we have small signal, we have to do these steps to make our analysis simple and straightforward. So we'll remove all DC sources and we'll just short circuit them. So what we're doing is we are taking all the DC voltage and we are opening the circuit for all DC current sources. And we replace diode by its small signal resistance. So when we do these two steps, our analysis becomes simple and straightforward. So we would replace this guy with this, and we just short. So if you look at this, all we are using here is just the small signal. We are not using VDD by itself. So VDD itself is not there. It's been replaced by a short circuit. And what we have here is now, as power supply is taken, just a small signal variation, right? And the current is now just the varying current, not the diode current as we wrote before. But now we have to find what is this current, right? With this new resistance that we are using. Let's take a look at an example. So it says circuit, for example, 4.5, which they're using for somewhere else. And what we have to do is, this is 4.5. Let me read up, what does it say, example? All right, so so the statement is that the circuit has R 10 kilo ohms. So R is equal to 10 kilo ohms. The power supply has a DC value of 10 volt, on which is superimposed a 60 hertz sinusoid, 60 hertz sine signal of 1 volt peak amplitude. This signal is an imperfection in the power supply design. It says this is the imperfection which is writing. It is known as the power supply ripple. Calculate both the DC voltage of the diode and the amplitude of the sine wave signal appearing across it. Assuming the diode to have a 0.7 volt drop at 1 milliamp. So diode has 0.7 volt drop at 1 milliamp. So what is the DC voltage and amplitude of sine wave signal across this diode, right? So if we if we had just DC here, if you just were dealing with DC, which is this case, what would be my diode current? All right, tell me, what would be my diode current? Can somebody help me write the relation here? What would be my diode current?
Would it just be the 10 volts divided by the 10K ohms?
10 minus 0. Yeah, you're right. We take care of the ground and the resistance. All right, very good. 1 kilo. And that's just 0.93 milliamp. And so this is close to 1 milliamp. Now, what is the diode resistance? Can we find out diode resistance from this? Remember how did we calculate diode resistance? Right?
VT over ID.
VT over ID. So can I find RD? What is VT?
It's 25 milliamps.
25 millivolts.
Millivolts, sorry.
Divided by this current that I just found. So that tells me my RD is 26.9 ohms. Right? So far, so good. So we start with DC. Of course, we need to find the diode resistance, which ultimately comes into play when we are dealing with small signal. Now, what were the steps? About 2 steps for the small signal analysis. Eliminate all DC sources and replace diode with its small signal diode resistance. Right? Let's do those here. When I do this, what I'm doing is I'm getting rid of 10 volts. That's a DC source. And what I'm doing is I'm using now the ripple or the small signal is still coming from here. So I need to keep it there. But this guy is gone. So this is a ground now, right? But there is still some value that's coming from this. And that value is, what was it? This guy, 60 hertz, 1 volt peak to peak voltage. You with me on this? Okay, let's plug in. And now, so this step is important for you to know how we do it. When you get rid of this, you are getting rid of the DC part, but not the signal. So signal is still there, but now there's no, it's not a source, it's a signal with respect to ground. 10 volt is now grounded in a way. So you could, okay, if you get scared with this, you could have just written it like this and shown the ground towards the roof signal, right? We might as well have written it like this. Agree with me? So what we have done is, instead of that, we have just made it, and this guy is the diode now. So now understand, going from center one to the right one, don't be scared about how it looks, but you have to apply your ground skills and show it like this. Now comes your node analysis, right? So there is a signal coming from here, some signal, but it's nothing but a node analysis. Okay, it's a voltage divider now. We all see it's a voltage divider. And our interest of voltage is across this guy. How do I write? Okay, so now this guy, we have to use its small signal diode voltage. So we write it as an average value. And we say, okay, signal, and they're putting a kind of cap on this. So my VD peak, because the input voltage is giving you peak. So they said peak. So I say VD peak now, because that's they haven't given me peak to peak. Or we could have converted it to RMS, and then we would have got the RMS voltage on the output, right? So whatever the input signal, we go with that. Is this voltage divider? Who's gonna help me write voltage divider equation here? All right, there's a question. How did you get 0.9 milliamp? Matthew, you didn't stop me at that time. Which, are you talking about this guy?
Yes.
All right, so, okay. So this is where we have, hold on, 10 minus 0 or 1 kilo. This should be straightforward. Yeah, let me see. Oh, sorry, it is not 0, it is 0.7 here. Yeah, screwed up. Sorry, this was 0.7. Who made me write this equation? It's okay. That's a learning point. It's 0.7. We have the diode there. For DC analysis, we could not ignore this voltage. All right. Matthew, thanks for staying awake with me. And Brandon, you tried that with me. Thank you. I think there's more learning in what we just did. All right, so that's where the 0.9 comes in. Now peak. Somebody help me write my voltage divider equation where I want to find voltage across this guy. All right, which voltage are we talking about? We're talking about Vs, which I said, okay, they're writing it as Vs cap. Help me write the voltage divider. So there are, let me clean this up so we know what we want to find out. When I look from the right side, there are two voltages and it's a voltage divider network and there is a signal coming in. I want to find the drop across this. How do I do that? So this guy divided by sum of these two. Voltage divider. Should we do some exercises on voltage divider circuits? Please help me so I know where we are. It's a ratio proportion thing. When you need to find out, I think maybe it's the configuration that's confusing you, which is easy to see here, but not easy to see there. So if I have to find resistance across this, and there are two resistances which are in parallel and there is a voltage, how do I find this guy? You take this guy divided by sum of these two. So that will give you how much voltage drop is going to occur across the resistance of my interest. That's what I want to find out. So that's the ratio proportion. Yeah, go ahead.
We were looking for the resistance of little rd.
Exactly, because these two are parallel. If I find, all right, yeah, let me take a step. So if I find resistance across these 2 points, that's exactly what my output is, right? So if I find this resistance, voltage across this, that's what my output is. That's what my VD is, the diode signal. Do you agree? The Kirchhoff's laws, you have voltage. If you have, all right, let's take a step back. So if I have, say, two resistances grounded, let's make it ground, and voltage across this point and this point and this point and this point, aren't they going to be the same? The voltage across here and voltage, are they going to be the same? All right, let me get to a bigger room.
As long as they have the same resistance.
Exactly. Now it's very important point. Yeah. So, okay. All right. Everybody agrees. Who said that?
I did.
Okay. I give me your name.
Oh, Nestor.
Nestor. Okay. What Nestor just said. Say this point. I have 5 volt, and this is R equals R. Both resistances are the same. So from here to here, and from here to here, what can you tell me about the voltage across these two resistances? Are they
The
going
same.
to, they're going to be the same? All right, fantastic. Now, if I say this one is R1 and this one is R2, how do I find how much voltage is across R2? How much drop is happening across this guy? So
It'd
now,
be
yeah, go ahead.
R2 over R1 plus R2.
R2 or exactly. Now, Brandon, you're right. Let me give you a simpler example. So suppose Elisa and I, we won a lottery. I don't know, $60 lottery. I pitched in $20, sorry, and the ticket was $6. I pitched in $2, she pitched in $4. How are we going to split? So we pitched in 2 and 4. What we won was 60. How are we going to find out? This was S, me, this was Elisa A. Now tell me how much Elisa gets from this 60?
She gets she pitched in 2 or pitched in 4.
She pitched in 4.
So she would get
$40.
yeah.
All right, how do we get there? We
66%.
get there 4 divided by 2 plus 4 times 60. Right? We found her ratio in the whole investment. Right? Make sense?
Yes.
And that's, I don't know, 4 divided by 6, some number times 6. How much you said that will end up to be? $40. So by intuition, by banging our head with books for so many 25 years for me and 50 years for me, we know that by now. Straight away, it's going to be 50. But I'm just walking you through the process, how we get there. So this is what is ratio proportion. Her ratio was 4 to my 2, 1. We could have do 1 to 2 here also. And then this would become much simpler, which would be 2 over 1 plus 2. But it's now same thing is happening here. For R1, I need to then find the, for any one of those. Let me clear this first. Okay, everybody got this example of winning the lottery? So give me give me a sign that you didn't get it without, I don't want others to know, but I want me to know. You can write me a private message so I know if you didn't get it. There's no embarrassment. If you didn't get it, I'll repeat it and go into more detail. All right. Now, nobody send me a direct message. It's okay, all right. So now it's the same thing here when we say voltage divider circuit. We have to find the voltage drop across one arm with spec, and it's not going to be independent of the other. It has to be the ratio of both of those. So same way, if this was 4 and this was 2, and I want to find voltage drop across R2, how much is going to be that? I say VR2. How much is that going to be? So I said this is 2 and this is 4 ohms, kilo ohms, whatever, mega ohms. What's the voltage drop across R2?
Across R2, it would be 4 over 2 plus 4.
4 over 2
0.3.
plus 4 times 5 volt, which is going to be split between those two, right? So again, 2 by 3 times 5 would be what? Let's do this. It would be 3.33 volts here across these 2 points, right? Now let me throw another spanner in this machine. Now I say I extend this here, and I just say there's just an open circuit. I say, okay, how much is the voltage here? What is V0 here now?
5.
No, this is in parallel to this guy.
3.3.
3.3. It just, you're taking a lead out and you're using a multimeter to measure it. That's all you're doing. That's what it means. Now, if I'm looking from this side, all I'm interested is this, and I'm showing it like this. Just I'm extending to one wire out. I don't have to extend the ground wire. I just show the ground and everything is at ground. I extend this one wire out of it and I say, okay, man, it's becoming dirty. Let me clean it. So all I've done is extended this cable and I say, okay, what is V0? It's the same thing, which is the voltage drop across R2, nothing else. All right. Now let's go back to the original. I jumped through many pages again. Why do I do this? All right, so I come back. Oh, we have done this. All right, no, this is what we were doing. So now I challenge you to the same thing what we just did on the next page. What is RD? Is nothing but a voltage divider. And I have to find this signal coming through this and how much is the voltage drop across this guy, while this is also presented to that same signal. It's the ratio proportion of these two. It's RD over R plus RD. How much that's the signal that's dropping across VD. Right? So it's the same voltage applied from this side all the way to this side. And both are grounds. So we are interested, how much is it dropping across this guy? And this guy is 1 peak to peak. That's what is given. This ratio is 2.68. So it's 2.68 millivolt peak. We'll call it like that. And that's a small signal. Are we together on this? All right, very good. All right, so I wanted to do this question where we were doing this. All right, for small signal, we say small signal because if we go into large signals, what's the time? It's time. I'll just give this comment and we'll stop. Large signals would then bring in capacitances with them. So we'll have diode capacitance, we'll have junction capacitances. Go ahead. Question?